Hello, hi all. Welcome to our February edition of the JavaSig. So today we are starting off a little early than our regular time. I hope you're all able to join in today. We have a special speaker with us today, Juan Femero. He's joining us from London. Really thanks to you, Juan, for making it today. I know it is so late in the night for you, probably like around 10:30, 11, and then probably that's really nice of you to make this time for us and come over to New York virtually today to meet all our guests and all our participants. Uh, so we have a really interesting topic that's going to be presented today by Juan. But before that, I want to make sure that you all are receiving all the updates that we publish on JavaSig. Hope you are following us on the Twitter handle at NYJavaSig on Twitter, and also please register yourselves on our website on javasig.com so that you get all our emails and all the communication and learn about all the latest events that are going to come up. And so today, so go ahead and on YouTube chat, feel free to put in where you are from, right? So that we know where you're joining us today from. And then let's quickly see what Juan has today for us. A few words about Juan before we hand it off to him. So Juan is a research associate at University of Manchester in UK, and he works on FPGAs and GPUs, and specifically he specializes in how to uh, how to run interpreted languages such as R or Java through parallelization and compile them and transparent execution in these GPUs and FPGAs, and JIT compilation and executing Java programs in this. So that is really cool, and he's working a lot down the tech stack and into the hardware. And before that, one obtained his PhD at University of Edinburgh. I hope I'm saying that right. On accelerating interpreted programming languages on GPUs and just-in-time runtime optimizations. So with that, I hand it off to Juan to kickstart our talk today. Juan, can you go ahead and share your screen?
Yes. Okay, hello everyone. Thanks for the nice introduction. So I hope you can see the screen. So first of all, thanks to the organizer for the invitation. It's a real pleasure to be here in your group talking about our project. So today I'm going to talk about, well, all of us know TornadoVM, but before going to TornadoVM, I'm going to first start with the reasons why we're doing what we are doing. So heterogeneous hardware now are everywhere. Mobile devices, smartphones contains multi-core CPUs and a GPU. Laptops contains multi-core CPU plus a dedicated GPU, quite likely also an integrated GPU. And even data centers, you will see more than this, right? You will see a lot of multi-cores, maybe a lot of GPUs, and also FPGAs, quite likely. All of this is because developers want to accelerate applications while reducing energy consumption. Even companies are providing their own customized hardware. For example, Google is providing new chips called tensor processing cores to accelerate deep learning applications. Or just to give you another example, GraphCore is another company that is providing their own chip, okay, to accelerate natural language processing algorithms. Okay, so that's great. We have a lot of hardware coming, right? But we need a way to program them. So it seems like for every new hardware, we have a new library, a new programming model, a new language, and so on and so forth. That's fine. That could be one strategy, right? But this makes applications hard to develop because you have to mix programming models, you have to mix libraries. It's hard to debug. It is hard to maintain, etc. Instead of doing that, in Manchester, we believe in another approach, and we took the same approach that Java, the same philosophy that Java has. So write once, run everywhere. And the question is, can we do the same for GPU and also for heterogeneous computing? Well, our proposal is called Tornado, and that's exactly what we do. So in a nutshell, what Tornado does is it's a plugin to OpenJDK. We focus on Java or JVM-based programs. It's a plugin to OpenJDK that allows us to run JVM programs on heterogeneous hardware, like multi-cores, GPUs, and FPGAs. And even more, we can do task migration, okay, between devices at runtime. That's a really cool feature what we have. So this is the agenda for today. I'm going to start by introducing a little background and terminology. So if you already know GPUs and FPGAs, many of the concepts are going to sound familiar. Just stay with me, and later on I'm going to explain you how you can use it from Tornado. If you haven't heard about GPUs or FPGAs, or you don't know how to use it, or key concepts, don't worry, you're still in the right talk. I'm going to just give you a highlight of the main concepts that are easy then to follow the rest of the presentation. Then I will focus on the main components of Tornado. I will show you how you can use it, how can you benefit from Tornado to accelerate your applications, and I will show you some demos, live demos for you. And then I will show you some performance results and some directions where we are going and what industry is, which industry and which companies are using TornadoVM for acceleration. Okay, so first of all, the motivation, why we are doing what we're doing. Do we need heterogeneity? Do we need GPUs and FPGAs? Well, I already spot the reason at the very beginning, but here I show you with some numbers, right? I show you here 3 different microarchitectures. CPU on the left-hand side, GPU on the middle, and FPGA. So let's take the CPU on the left-hand side. So the CPU in this one, for example, is Ice Lake microarchitecture from Intel. This one has 8 cores, hyperthreading, plus vector instructions called AVX, SIM instructions. And this CPU has also integrated a GPU. So if you count all of it, you can get up to 1 teraflop of performance. Let's take now the GPU, or the one in the middle. So one of the things that we notice is instead of having 8 cores, we see more cores. We see actually in this one, Pascal architecture, which is already a few years old, 3,500 cores. Obviously, the concept of cores is not the same as CPU core, but that gives us a hint at what's going on inside. So actually, GPUs are optimized for throughput, high throughput, rather than latency like CPUs. And for throughput, we need a lot of cores. And that gives you, for example, if you compute in floating point precision, single floating point precision, you can get up to 10 teraflop of performance. That's really high. Right? And similar situation applies for FPGAs. So in this talk, I'm gonna talk a lot about GPUs and FPGAs. So let's set up some terminology. So GPUs stand for Graphics Processing Unit. And GPUs has been traditionally used for graphics rendering. The thing is, to do the rendering, GPUs implement in hardware a pipeline of operations. For example, compute vertices, compute geometry, compute textures, and so on. And researchers some years ago realized that some of these stages can be used for general purpose computation, not just rendering. For example, you can run matrix multiplication, or any deep learning application, or physics simulation, or fintech simulations, or Bitcoin, for example. And that's where the term GPU computing come from, and OpenCL and CUDA come from. Basically, OpenCL and CUDA are programming languages to program those devices, GPUs. So I want to highlight 2 things here. First of all, the first difference I already spotted. The first difference with CPU is number of cores we find here. GPUs classify cores in groups they call stream multiprocessor, or compute units, depending on if you take the CUDA terminology or the OpenCL terminology. It's essentially a set of cores that can operate the same variation together, and they can share the same memory. The second difference is on CPUs, most of the area in the die area, if you take the chip, is dedicated to cache. While on GPUs, most of the die area is dedicated to logic. This makes GPUs very powerful processor for compute. And actually, the type of applications you can target is different. GPUs are optimized for throughput, meaning I don't care to run a single element, let's say, faster. What I want to do is to run a bunch of them really fast. So I compute, let's say, gigabytes per second or X operations per second. That's why I care, right? While CPUs are really good at optimizing latency, low latency. So that's the difference in architecture. But why I'm telling you this? Because to program GPUs, you need to know architecture details, right? Let's say you pick CUDA or pick OpenCL, you normally need those. For example, I can give you a quick one. If you are sharing data and you locate data in L1 cache, you can do it in OpenCL. L1 cache is not coherent. So that means that the programmer has to add barriers to make it coherent, right? To make the result consistent. So those are little details that obviously the developer needs to know to program those devices. The thing is, well, we can program on top of OpenCL, and that's what Tornado does, right, actually. So Tornado is a framework on top of CUDA and OpenCL that we can hide all these, architecture details. Okay, let's talk a bit about the FPGA. And I believe this is more unknown for the Java community, perhaps. It's kind of growing, this community now, the FPGA in large audiences, let's say. FPGAs stand for Field Programmable Gate Array. And in a sense, it's like you get the hardware and there's nothing you can run on it after manufacturing. It's up to the user what to run. And for that, the FPGA provider gives you, or the FPGA gives you what is called logic slides, basically lookup tables and or short, very low level, plus programmable memory, VRAM. And normally FPGAs vendors give you specific functions, for example, DSP for digital signal processing. And you can use all of it to physically wire your algorithms into hardware, right? And I'm gonna give you an example how you can do that right now. You can use something like Verilog or VHDL. Those are very low level languages. You program at the gate level. This code, I'm not gonna go into the details, is showing how to program half other, A plus B. So you define your entity, which means how many inputs and outputs you have, and then you define what to do with your inputs and outputs. So for the sum, you need a SHOR gate, and for the carry, you need an AND gate. And then this is physically translated to hardware, right? Okay, good news is many vendors from FPGAs are providing high-level abstractions. The one is OpenCL. So you can target, let's say, OpenCL instead of Verilog and program the FPGA. Why I'm telling you this? Because Tornado actually targets OpenCL. So we can go through the FPGA, or we can go to the FPGA through OpenCL. Okay, so in an ideal scenario, this is our vision, okay? We want to program, or we want to access and accelerate high-level applications, okay, on heterogeneous hardware, GPUs, CPUs, multi-core, and whatever new hardware comes along. And to do that, we provide what we call heterogeneous virtual machine. It's a virtual machine that is capable of offloading code to the correct platform and execute it efficiently. And even more, doing the task migration. Okay, with this, let's go to some internal details. Let's dig into the TornadoVM project. And in a nutshell, TornadoVM, I said at the beginning, is a plugin to OpenJDK, right? That allows Java developers to use heterogeneous hardware, GPUs, FPGAs, and multi-core, and also perform task migration. So TornadoVM can run with main vendors from OpenJDK, JDK vendors like OpenJDK 8, OpenJDK 11 until 14, for example. We can run with proliferation, Red Hat Mandrel, or Amazon Corret. We can run also multiple operating systems and so on. One other thing I want to highlight is this project came from the university. So it's a research project, okay? It's not a product. Just something to keep in mind. Okay, so let's dig into that. So how do you use Tornado? How can we run something in Tornado? For that, Tornado provides an API. And the API is quite simple. It's very simple, actually. It provides what we call tasks. You accelerate tasks. Each task is the equivalent of a method, Java method. So we accelerate at the method level, like hotspot, okay? And Okay, so you can accelerate methods in isolation, or you can say, when I want to accelerate a group of methods. In that case, we create what we call a task scheduler, basically a group of methods that you want to accelerate. So this identifies the region, okay, of the code to accelerate, but it doesn't say anything about how to parallelize. So to do that, we provide two annotations to the user, Java annotations, that can be used in your code to annotate, to say, please parallelize this loop. This loop is candidate for parallelization. Don't worry for the details. I'm going to give you a few examples later on, step by step. This is just a high-level overview. So once this is API, once the programmer writes with the application with this API, we pass to the Tornado runtime. So the Tornado runtime will get all the methods that are grouped in the task scheduler and will optimize data flow. I'll show you an example on the right-hand side. So each node represents how data is flowing, and the square represents computation. And the reason is because GPUs and FPGAs usually don't share memory with the main CPU. So we need to allocate memory on the device and do the data transfer. The data transfer is the key because it takes time. It's going through PCI Express on the machine. And this takes time. So if we can save data transfer, that's a way to even speed up more the application. And that's what the data flow optimizer does. Basically, figure out how many variables you need, which one you want to keep on the device, which one you want to take out, right? For getting the results. And then from this graph, we generate our own bytecodes, Tornado bytecodes. This is just a way to orchestrate execution. Basically, the bytecodes will tell us, allocate this buffer on the device one, do the data transfer of this variable into the device one, the GPU, launch a method, which means the first time we launch a method, we compile that method down to whatever we have available, either OpenCL or PTX. And for the compilation, we extend the Graal compiler. Actually, we have our own phases. We have our own optimizations that we extend from the Graal JIT compiler in order to generate either OpenCL code or PTX code. In this case, I show you PTX. PTX is the, let's say, intermediate representation of CUDA programs. Right? We go down to that level. And once we get this code, we install in a code cache. So if the same expression is encountered again, we just reuse it, right? We don't have to recompile. Same as Hotspot does. I think we have a few questions. I'm happy to take them. If you, Barry has told me, we can handle some questions now.
I don't see any at this point, but I will keep you posted if we do.
Okay. I just saw your message. Okay, so I can continue. That's fine. So with that, we can run, so we have two backends, OpenCL backend and PTX backend. And with OpenCL backend, we can target any OpenCL compatible device. For now, we have support for NVIDIA GPUs, Intel integrated graphics, AMD GPUs, Intel FPGAs, Xilinx FPGAs, multi-core, AMD multi-core or CPU from Intel multi-core, and also our Mali GPUs. And for the PTX backend, is PTX proprietary for NVIDIA, we can target NVIDIA GPUs. Right? The thing is, sometimes it's faster the one to another, right? So we can target NVIDIA either from the PTX backend or from the OpenCL backend. Right, in fact, okay, enough theory, let's start with some practice, right? I'm gonna show you one example, it's called the DFT, Discrete Fourier Transform. The reason I show you this code is, it's pretty simple, it's in Java, it's just a few lines of code, and it's easy to show performance as well. And this application can be used for, well, it's widely used actually for digital signal processing, spectral analysis, data compression even, and so on. All the examples I'm gonna show you today are available on GitHub. And you can see the code, you can even reproduce it if you want to. There are instructions how to install it and how to run each application. So let's start with the DFT. So you start by prototyping like normal Java code. This is the Java implementation. Let's start with the Java code. So we have a class called app, and we have a method called compute_dft. We pass the normal parameters for this method, and then we have two for loops that are going to correspond with this. So for each item, we need to compute this formula in a sense. So we have two for loops. For each item from the input, we compute the sum. And each, in the inner loop, the sum is the input by the cosine of an angle and the input by a sine of an angle. But it doesn't matter too much. It's just to show you a quick example, right? So the first thing to do, if we want to run with Tornado, is to annotate the code. So the user thinks, the first loop can run in parallel. So let's add the add parallel annotation there. That means that there is no dependency across iterations. So the user believes that this code can be parallelizable. What I'm saying is, even if the user writes at parallel, Tornado will double check that we actually don't have dependencies. Because if we have dependencies, Tornado will bail out and execute the sequential because it cannot be parallelizable. So that's what is called relaxed parallel semantics. So once you do that, then the other thing is to identify which methods you want to accelerate. And you do this via the task schedule API I showed you, or I told you before. So you build an object called task schedule. You give a name, could be any random name, a 0, DFT, whatever, it's just a string. And then you compose tasks. You can compose as many tasks as you want, task. Each task receives a name. Again, could be any name, could be full bar, any name. And we pass a reference to an existing Java method. In this case, it's the class app method compute_dft. And then the rest of is the correspond with the normal parameters, okay, for a method. And then we have a call called stream out that says, okay, I expect the output in these two variables because memory is not shared across the GPU and CPU. We need a way to synchronize the data to getting back the results from the device, the FPGA or the GPU, back to the Java side, to the Java heap. And we do that through the stream out operation. And then we call execute. So once we call execute, then we start compiling the application for you down to either OpenCL or PTX and run it. Right? I want to highlight another thing. So this is pure Java. The kernel, the kernel, we mean the code that is going to run on the accelerator, that's compute kernel. There is no differentiation between the kernel and what is not kernel. It's the same language, it's the same file, can be even the same file, okay? That's what is called single source property. OpenCL is not single source property, CUDA is not single source property. There are different languages. The kernel is another language than the host language. There are other, like SQL, for example, follows a single source property. I think we tend to do this now. We tend to simplify by just providing a single interface through the single source property. Okay, and then to run it, we just type Tornado and your program. In fact, we type Tornado because we are lazy people in our group. It's just Java, okay, plus a few parameters to enable Tornado, Java parameters. I want to show you in a bit. Well, I'm going to show you now. So let's run it. So what I'm going to do now is I'm going to run the application with Tornado. So remember that you can find this example in the repository I show you. The code is online, you can read it. But anyway, I'm going to explain in a bit. So I run the Tornado command, and I say the class is this one, DFT is the program. The first parameter is the input size, and the second parameter is a flag that is going to tell me, yeah, I know you're running with Tornado, but don't create the graph and don't call execute, just run Java, okay? And then the last parameter is the number of iterations when I run the application. So if I do that, it's going to take a while. So in order for you to trust me, I'm going to show you, while this is running in background, I'm going to show you the real code, okay? So this is the code I'm running. This is the compute_dft. It's very similar to the slide I show you. We have one loop here, another loop here, and we have the actual computation over here. So if I go to the main, okay, I have the input parameters, size, a flag telling it's tornado or not, and the number of iterations. And then if the flag is not the sequential flag, okay, I don't build the task schedule. I don't build anything with Tornado. And when I execute it, I just call the method as it is. So it's running with Java, okay? And if I call with the Tornado flag, so it's not sequential, I'm gonna build the graph and I call the graph.execute. So I'm gonna accelerate that method. So let's take a look what we got. So this application is taking around 30 seconds, 26. Well, take this number with caution. So to do a proper benchmarking, you need to run it with a proper framework like Java MH or something like that. This is just to show you a quick demo, okay? I can tell if you run this for a while, this goes down to 19 seconds approximately, right? But I'm not gonna wait for this. This is taking too long. So what I'm gonna do is I'm gonna stop the process and I'm gonna enable Tornado. So I pass the flag Tornado and I'm gonna run it. Boom, finish. Each iteration is taking 8 milliseconds. So I went down from 20 seconds, let's assume the time is 20, not 30, okay? Down to 8 milliseconds. And you can say, no way, you are doing something, this is not right. Okay, so we can tell Tornado to give us some debug information. What are you doing behind the scenes? And in this case, if I enable the flag, it's telling me, you're running on the NVIDIA GPU 1050. That's the NVIDIA GPU I have on my laptop, this laptop. In fact, we can also print the kernel that is auto-generated. So Tornado will generate kernel. In this case, it's going through an OpenCL platform. So we should see an OpenCL kernel. And if I do that, the kernel is generated only the first time, and that's the actual code we generate. So it's compute DFT, that's the same name that the Java method has, and it's pure OpenCL, okay? We don't have to go that deep, but it's just to let you know that we're using Tornado. We're using FMA instructions even, it's an optimization. We will talk more later on about this. And we can also change the device. So remember that we gave names. Let me show you the code again. Here, no? S0, T0. I call it S0, T0, but you could put any name. So that's what the names are useful. Now we can say run on another device. And which device? Okay, so Tornado has a command called tornado/devices. And this will print all devices available for Tornado. So the default one is the 00. That means backend : device index. Backend is OpenCL backend, and this one has 4. It's the NVIDIA GPU, 1050, sorry. Then one is using the AMD driver, but run on a multi-core system with 8 threads. Then the second one is an Intel graphics, HD graphics. The last one is an Intel CPU using the Intel driver, multi-core. And then there's another one here, PTX, and it's only one device. And this is going through another backend, the PTX backend. So we can select the backend we want, right? So let's do that. Let's change the device. So remember the names we put. So we can say, please do S0, T0, device. Let's pick one. For example, I don't know, integrated graphics, let's say 0, 2, okay? I'm gonna print also with debug info. And now it's telling me, we're running now in the integrated graphics. Look at the time, it's a bit higher compared to the GPU because this is a low power GPU, okay? The Intel one is integrated inside the CPU. We can also use the multi-core. Let's say we hold the number 3, which is a multi-core. And automatically we get a multi-thread application running. We express this Java sequential program, by the way. Or we can say, please use the PTX backend instead, which is the 1.0. And if we use the PTX, boom, it's actually faster. It's 4 milliseconds. It's faster, or 3 milliseconds. It's faster than the OpenCL one. And this is the code we generate for you. So now it's not OpenCL anymore. It's PTX. Okay. Okay. I hope I convinced you that Tornado is useful. So let's go back to the presentation. In fact, I have some demos missing. We can also use the FPGA. So to do that, I'm going to show you two demos, exactly the same application, DFT, but running on the FPGA. And I'm going to show you also another application, Black Source, just to tell you that Tornado can target many domains. So DFT, let's say, is in the physics domain or digital signal processing domain. Black Source is in the fintech domain, let's say. All this code is available online, by the way. So I don't have, unfortunately, an FPGA on my laptop, but I have access to a server. So let me clear for you. So if I do, again, tornado//devices, let's see what we get here. We have a powerful GPU, GP100. We have a multi-core. There it is. We have an FPGA from Naratech. Naratech is a vendor, but it's an Intel FPGA. So let's use it. To do that, let me just run. If I have the command, yeah, there it is. So I'm gonna select device 2 because that's the device of the FPGA. I'm gonna run with debug info just to print me where you're running. And in the case of the FPGA, I can pass a configuration file. This is because one thing I haven't told yet is to compile OpenCL to the FPGA, I need 2 hours. Okay. Why? Because we go from Java to the OpenCL, that's a matter of milliseconds. And then we call the Intel tools that transform the OpenCL into actual binary bit stream configuration, is called, for the architecture, for the FPGA. This process takes time because it has to rewire, it has to figure out how to route the application into hardware. And for this takes time. So what Tornado can do is either compile it, everything in JIT mode, you have to wait 2 hours to get the result, or you can use a precompiled one. So I precompile for you. And I can specify what's a precompiled one through a configuration file. That's the only thing. And the rest is the same. It's the application, input size, I'm calling Tornado, I'm calling 5 times, for example. So if I run it, interestingly, so this message, reprogramming device, is a message from the FPGA that is telling me I'm loading the bit stream, the binary, into the FPGA. And now you can see that the application on the FPGA takes around half a second. So compared to the Java one I showed you before, like 20 seconds. It's a huge speed up, right? Right, so now let's go to the fintech application. I have here the source code, let's have a look. So this one is from the MD SDK we adapted for Tornado. And again, it's Java, okay? You write Java. The only thing is we add the notation and we build the task graph over here, okay? We can say stream in data, stream out the output, and we call one task with this method. And the output is the prediction. Well, I'm not an expert in fintech. Many of you probably are. But basically, it's a prediction of 2 values, no, in the stock price, call and put is called. So let's run it on the FPGA. Again, I precompile it for you. We don't have to wait 2 or 3 hours for this. So if I manage to find a command, okay, I can have my notes over here. Just a second. There we go. So I'm gonna run with this size and 5 iterations. Again, device 2 and the configuration file that I precompiled the code. So if I run it, that's the code, that's the bit stream loading, message reprogramming, and the application already finished. And for this application, I'm waiting a bit of time. So I'm running, so the application on the FPGA already finished. And now it's validating the result. It's running the sequential a few times and validating the result. So while we wait for the validation, I think we are at a good stage for handling questions, if we have questions right now. Do we have any questions for now?
So I didn't see any questions, Juan, but I did, other than my own, about Project Sumatra. How does this relate to Project Sumatra?
Right, so Sumatra, well, the project Sumatra is closed already. It was an early project by AMD. And the goal was to run Java Stream 8 API with Etsail. Etsail is like equivalent to PTX. For heterogeneous hardware. So you use they use the acceleration of for each method in the Java 8 Stream API, and only that method to go down to the accelerator, to get down the code to the accelerator. We provide our own API, so we differ from them. They didn't use Graal at that. I think, no, they used Graal. They started using Graal. But instead of OpenCL, they generate Etsail, right? But the API is different. They don't have task migration. They don't have specialization. It's something a technique that I'm gonna tell you in a bit. I'm gonna show you in a bit. But pretty much that's it. Actually, Sumatra was, I think, was an inspiration for many of us. So I did also my PhD on this topic. Sumatra at that time was the project based on, and Tornado is also based on ideas created by Sumatra project.
Oh,
but
wow.
I think that's how it's related, right? But the project's already closed. Yeah.
There is another question from Victor. Do you have plans to support wrappers like the object form of integer or long, capital I, capital L?
Right. We don't have plans for that. We support some objects already. The ones we know the data layout, we support, obviously the format, arrays are the good format for GPUs. Apart from that, we support some custom vector types because we can use vector units. We don't have direct plans to support long, the grabbers libraries, but something we can, if the community need it, something we can talk, yeah.
I see. Jonathan had a question. Is the 2-hour compilation more of an issue with FPGAs, or is it also the problem with cost with GPUs?
No, this is just for FPGAs. So actually, the demo I showed you before was everything was on the fly, right?
Right, nice.
Yeah,
okay.
Yeah. So let me just wrap up. Maybe it wasn't clear, but let's remove the debug info just to focus on the timing. So if we look at the first time, the first iteration takes 300 milliseconds to compile. This is because we get the code, we specialize the code, is something I'm gonna talk in a bit, and then we compile the code to PTX. Then from that iteration, goes down from 300 milliseconds to 3 milliseconds. We don't have compilation at this point, right? So the first time, if we're running on the FPGA, instead of 300 milliseconds, it's gonna take 2 hours. This is I don't know if I call it an issue. I don't know if it's possible to speed up the process. I know that Intel is releasing, and Xilinx as well is the same thing. Every new version is speeding up the compilation process from OpenCL, but it still takes a long time. This is because the synthesis, okay? We need a way to, from the language, from the OpenCL source, go down to the actual configuration file, register wires, logic gates. This takes time.
I see. Interesting. Yeah. And I know that since a lot of us have Macs, doing things like, GPU work on Macs has been problematic for several reasons. But recently Apple has the M1 chip. Were there any plans to support the Apple M1 chip?
We don't have direct plans. We are not supporting a new platform. Well, not new platform, a new, let's say, set of tools by Intel. It's called SpearV and One API. That's where we're heading now. But directly with Apple, we don't have any plan. Maybe a Metal, we have some internal discussions about this. But direct plans right now, no, we don't have those.
And that was the last question. So you can go back to your presentation if you want.
Okay. So thank you for the questions while we wait for the results. So remember, I was running the Black-Scholes application on the FPGA, and the sequential take took around 10 seconds each iteration. Please handle with caution. Maybe it's a bit down than 10 seconds. Just a quick demo to show you now. And the parallel implementation took around 0.7 seconds. So not even a second. That gives you a speed of 14x, okay, to run a fintech application on the FPGA. So I want to highlight one thing. So you saw the code. The code was Java and was sequential Java. We didn't specify at the source code level any annotation regarding FPGA, GPU, or CPU. We can run the same code everywhere, same as Java. Okay, so let's continue. In fact, because I show you a quick demo with FPGA, I want to highlight some results from an actual setup for benchmarking. So we have a publication by one of our students, Michalis, and I show you two graphs here. The first one is compared to Java hotspot. The second, the one on the bottom, is compared to Java multithread. And I show you performance. So the higher, the better. And I show you for different applications. For example, if we take Black-Scholes for different data sizes, so each bar corresponds with a different data size, small, medium, and large. We see speedups up to 15x. Or if we get DFT, we see a speed up of up to 200x, more than 200x performance. That's a lot of performance. If we take multi-threaded, so the user wrote a Java multi-thread application and we compare against that, we can get a speed up to 20x for DFT or up to 2x for Black-Scholes, for example. I want to comment just a few things for all the data sizes. So as you can see, for small data sizes or medium in some cases, we don't get speed ups, and that's expected. That means that because we have to allocate a buffer on the device, many buffers actually, and do the data transfer, if we don't have enough elements to compute, that means that the bottleneck is data transfer is not compute. So we don't expect speed ups, right? So in other ways, don't go to the GPU of the FPGA if you don't have enough elements to compute, basically. But Tornado has a way to handle these cases. I want to explain you at the very end of the presentation. Okay, so let's continue. Just a few words about the FPGA, just to comment out this, why we need 2 hours of compilation. We already targeted that with the question, but I had the slides for that. So we go from the Java bytecode, down to OpenCL. And then we call a second stage of compilation that we call directly the provider tools. For example, if we use Intel for FPGAs, we call the AUC tool. AUC is a compiler transform from OpenCL down to the bit stream. That's binary, that is a configuration file. If we select Xilinx, we can run on Xilinx. The tool is called XOCC, okay, Xilinx OpenCL C compiler. And that's a process that takes a long time, right? But Tornado has a way, as I show you, right, to plug in the pre-compiled ones. And that's why we can get fast loading time, let's say. Okay, so now I'm gonna show you a few things about what's coming in Tornado. So Tornado, we're expanding the API, actually. We believe as it is actually simple. So I show you basically, 70% of the API. You can get a lot of code just by, prototyping your tool, your application using this API. But we're expanding with more things. One other thing is, right now we have what we call loop parallelism. That means that the user annotates loops that they think they're parallel. That's called loop parallelism. We're expanding the API to also support kernel parallelism, meaning that the user can write, apart from loop parallelism, if they want to, the user can write the work per thread, let's say. This is the same model as CUDA, OpenCL, SQL, all these languages, right? And why we're doing this is because we are detecting that many users are coming from this domain, from OpenCL and CUDA, and it's very easy for them to just write the same kernel in Java. But for the Java users, writing that type of code might be difficult to learn and to understand. I'm not saying it's just impossible, it just takes time to get there. So that's why we keep both. We keep the loop parallelism style, which is really simple, and the one that we are building for kernel expressions, the kernel parallelization. And this gives us a very powerful API for the following reasons. This API, you can express the main 3 types of parallelization, of parallelism. We can express data parallelism, meaning compute the same amount of work, let's say the same computation for different data items. This is perfect for GPUs, okay? We can also integrate task parallelization, meaning I'm gonna run different tasks. Each task is running different code, right? And I can run them in parallel. This is because we have task or task or task. Each task could be unrelated to each other. And we also support pipeline parallelism, meaning that if there is a dependency between tasks, we can pipeline and then communicate and compute at the same time, basically. So it's overlapping communication with computation. This is a technique called pipeline. And with this simple API, we can express the 3 types of parallelization. So in a sense, it's high level because allows users to just write Java code, sequential code, and you get the parallel code quickly, and you get reasonable speedups quickly. And it's also low level enough to get more information out of it, like kernel parallelization. You get access to barriers in OpenCL and CUDA. You can get access to allocation and L1 cache if you want to, but it's not a requirement. So if the user wants to keep the simple one, it's perfectly fine. So just to give an example of how this looks like. So remember, this is the loop parallelization. For example, this is a simple vector addition. You have a for loop and you add the 2 vectors, easy. We can express the same using the kernel parallelization. And you can say we pass a context and then get a context, a thread identifier from the context. So give me my thread ID and I computed my element, right? For many developers, this is a more natural way. You can just pass lambdas and express the same thing like map reduce style. And for the developers, they prefer the other way. So right now in Tornado, we can do both, right? That's coming next month. Okay, so we can also run Tornado, I'm gonna say just a few words, on top of GraalVM and Truffle. And that gives us access, so you can access TornadoVM from Python, R, Ruby, NYJavaSIG, whatever language is supported on top of GraalVM. We do this through a component in Truffle called Polyglot. That is a component that they can talk each other. So basically it's an EST, a common EST across languages. And the code you write in Tornado is Java, okay? Because those languages are implemented in Java, it's easy to communicate from that language to TornadoVM, meaning that you might have a Python program for machine learning or deep learning, and you can call Tornado for running on the GPU or on the FPGA. I'm gonna show you here an example. Let's say you have your Java class compute, right? And you build your task schedule. So this is a sketch, okay? It's not a complete example. If you want to call it from R, Python, or Ruby, you just, from the language, just import the Java types, and you can call your class.compute. Similar for Java or similar for Node.js, right? In fact, we have a demo last year in QCon London running Node.js on the web browser on the GPU. So if you are interested, just check out. So really, this is important because out of the box, this is thanks to Truffle Polyglot, right? So they did a really good job integrating those languages, and we can benefit from it. So if you have code already written for Tornado, you can just use it in any language on top of VM, right? Okay, so at this point, I finished what we call this API and what the user needs to know in order to use Tornado. Now I'm gonna switch into a second part of the talk. Here we explain the internals of TornadoVM. So how TornadoVM actually compile code down to PTX, how to optimize code, and how the code can be migrated, between devices and so on. So I have to say that Tornado does this automatically for you. You don't need to know these details, right? So this is for, let's say, compiler enthusiasts like us, right? That wants to know every single detail, how it's done, how it's implemented, and so on. So, but keep in mind that the work I'm gonna show you now, everything is transparent. So Tornado will do it for you in a transparent manner, okay? So in a nutshell, what Tornado does is, okay, you get the Java code. We have a blue box here. It's the Tornado JIT compiler that takes a runtime, the Java bytecode. We compile at the bytecode level, bytecode down to OpenCL and PTX. And with that, we can use any device accelerator. So let's open that blue box. Let's see what we find there. So we have the data flow analyzer. Basically, remember that is a component that takes track of how variables buffers are used across tasks, so we can optimize data transfer. We have a big component for the runtime that orchestrates execution, creates the buffer for you, allocate memory, synchronize, compile the code, launch, orchestrate the compilation, and so on, and even orchestrate how tasks are migrated. That's a core component, the runtime. And we have a big component for the JIT compiler. And the JIT compiler is I already said that, is an extension of the Graal JIT compiler. So if you know Graal or you're interested in Graal, many of these concepts will sound familiar to you. So Graal internally divides in several, let's say, group of compilation phases or group of tiers, if you like. It's the high tier, which high-level optimizations. For example, loop unrolling, parser script analysis. This could be located in the high tier. Then we find a middle group of memory optimizations. So, an array access is dividing into, base and offset. In the high level IR, we will see something like array access or something like that. But in the mid level, we will see something like offset, so base and offset addresses. And then we have a final set of optimization for architecture-specific optimization. For example, one could be FMA optimizations, fuse multiple add. That's actually depending on the architecture. If the architecture supports that instruction, we can generate it in that level. In fact, I'm going to show you an example in a bit. One other thing we do is specialization. And this is important. So either we target OpenCL or we target PTX, we need to specialize the code. What does it mean? The code we generate for GPUs is different than the code we generate for CPU or FPGA. Otherwise, we don't get performance, or we don't get the performance we want. This is because OpenCL is a standard, okay? It's a Kronos standard, meaning that code is portable across devices. So we can run the same code on an FPGA, on a GPU, or CPU. But performance is not portable. And in fact, for some architecture like FPGA, if we don't specialize, we don't get performance at all. Right? So we have to massage the code to get the optimization or the performance we're expecting. And this specialization happens in the compiler level. And I'm going to show you an example now how the compiler builds those optimizations. I'm using the tool called IGV, Ideal Graph Visualizer. It's a tool provided by Oracle OTN that you can use for looking at how Graal, for example, compiles code. And because we base on Graal, we can also use it for our own optimizations. So let's dig into that. So what I'm going to do is I'm going to click here. I'm going to run IGV. I'm going to load it. You can download this from Oracle 8 OTN. Right, so it's expecting something, right? So let's run the application. And the application I'm going to run, I'm going to simplify because now we're going to see compile graphs. And this is hard to see, right? It's complicated. So what I'm going to do is I'm going to compile very simple expression, vector multiplication, okay? So let's see. Let's use this command. And let's run it. In fact, we don't need the debug, let's say. So to use the IGV, the debugger from Graal, or the graph debugger, we use Tornado with IGV flag. Right? If we do that, right, apparently nothing happens, but if I load the IGV, we see things here. And what we're gonna see is the compile graph, internals of the compiler, the JIT compiler. How we compile code down step by step, optimizing and compiling code step by step from Java bytecode down to OpenCL. So let me show you, we call Graal and then we build a graph. This is called a control flow and data flow graph. So it's the same graph. Believe it or not, this graph is the same, represents the same as this code. It's just different representation, right? So for a compiled guys like us, we prefer this graph because it's an easy way to optimize. How we optimize? We just replace nodes, insert new nodes, create new nodes, replace new nodes. And this is a very powerful tool. So let me explain what it is. Don't get intimidated. Let's just get step by step. So red line means control flow. For example, loop begin, array length, give me the length of an array, an if condition. So I'm doing a loop for for 0 to n. That's an if condition to evaluate the end of the loop. And I'm getting data from an array. So I'm loading some data, load indexing. I'm loading array A, array B, and I multiply those elements and I store in the element in another array. So that's what it means, okay? So don't worry, don't get into details. Let's get the big picture. And what we see is a lot of compilation phases. So what we do in Tornado is we interleave Graal optimization or Java optimizations with Tornado optimization. We have a lot of optimization. We have around 150 optimizations. We can pass typical optimization in compiler, like loop unrolling, escape analysis, parcel escape analysis, concept propagation, this kind of stuff, plus our own. For example, if we see a loop that is parallel, we might replace it or add information to parallelize it and generate the parallel code in OpenCL. So let's look at that. So we have a phase called API replacement, and this is how the graph looks like. This is before and after the optimization. So if I do this, I can see what Tornado is doing behind the scenes. It's doing, I have a for loop begin, and the loop is parallel because the annotation was parallel. So what Tornado does is it's gonna insert some information for later generate the right code, the parallel code. It's gonna insert a range node, offset, and stride. This is our known nodes, okay? We build it on top of Graal. And well, we have many optimizations. We have, for example, data flow. Some phases don't change anything. We just analyze what is in there for later on, right? And then we have a big chunk of optimizations. Remember, high tier, high level memory is the high tier, is the beginning of the high tier, mid tier, and low tier. I'm not gonna go into the details, but let's have a look at one that I'm gonna show you. FMA. FMA is an optimization for architecture dependent, right? So if we have an operation A multiplied by B plus C, then this can be replaced with an intrinsic in the target language in OpenCL, for example. And let's look at this graph, what it does, right? This optimization. So if we take this, everything is white. That means that this optimization didn't do anything, right? Why? Because the code didn't use A by B plus C. But let's do it. Let's see what we get. Okay, so now we expect, it's floating point. Now we expect that the compiler will generate FMA. So, okay, I have to recompile the application quickly for you. No tricks, I'm doing this on live, hope it works. And I run it with IGV again. Right? Well, interestingly, I see the FMA instruction. Let's see the compile graph, what it does. If I look at the graph and I look at the same phase, I'm going down before the optimization and after the optimization. There we go. So the operation, the multiplication followed by an addition, those nodes were removed and we insert a node called OpenCL FMA. And then I have to say that once we optimize the code, everything we can, we just have a visitor in our pipeline in the runtime that traverses each node and generate OpenCL. Because this is FMA, it will generate FMA instruction. This is pretty much our work. Our work is just taking optimization here and just inserting nodes, replacing nodes, and so on. In fact, this is Graal, so you can build your own optimization for Graal if you want to, or for Tornado if you want to, right? And that's very interesting. I hope you find it exciting. Okay, so let's continue. So now that we somehow understand the compile graph, bear with me, this is fully transparent process in Tornado, right? So you don't have to understand these details. This is just for enthusiasts like us, right? For FPGA, if we don't do any specialization, we don't get any speed up. In fact, we get slowdowns compared to Java. So what we do is in the graph I show you, we insert attributes for scheduling, how many threads you want to run. We say running blocks of 32 by 32, things like that. In the graph, in the compile graph. We specialize the loop unrolling. Then we specialize the loop flattening. So basically do loop flattening. By doing this process, we pass from a slowdown to 220x performance on FPGAs from Intel. In fact, we have a publication that you can check, how it's implemented, all the details and so on, if you're interested. Okay, so if we have time, let's switch to something very exciting. This is something that's missing in many frameworks. It's called a live task migration. So how Tornado at runtime can migrate a code running on one GPU to another GPU, or one GPU to an FPGA. So I hope at this point I convinced you that Tornado can run on many devices. I already execute on FPGA, on GPU, multi-core, on integrated GPU. So what we do is the following. Tornado can spawn a set of threads, as many threads as devices are visible on the system. And they're running in background. And we keep one thread as the master thread for running the sequential application. We need to do this because we need to guarantee that the execution makes progress. But in background, what we do is we compile, specialize, and generate the code and run the code for each device. And then we have, in fact, what is running is an instance of the TornadoVM. So each thread will run an instance. TornadoVM, as a recap, is a small component in Tornado that can allocate memory, launch a kernel, compile down from Java bytecode to OpenCL, OPTX, and so on and so forth. So each thread has its own VM, TornadoVM. And that TornadoVM is running on the CPU, like a Java process. And then we have a decision logic that says, oh, I know you are running on the CPU, Tornado will tell us, but if you switch now to the GPU, you might get faster or more efficiently. Now, how do we do that? Well, it depends. We have what we call policies. So we have 3 policies now. We have end-to-end policy, peak performance policy, and latency. So we call execute and we pass the policy there. And the difference between them is as follows. So end-to-end and peak, these two, will wait for all the devices to make a decision. And the end-to-end will encounter also JIT compilation. So the JIT compilation plus the time that takes to run on the device. The peak performance will not encounter JIT compilation, only the pure execution. Because these two wait for all the devices, this is a huge overhead, right? The thing is, if we switch, we know that it's faster than the Java thread, right? Then we have another mode for low latency. And basically what it does is the first device to finish, just switch over it. Just run, just go for it, right? This is well suitable for short applications, like short running applications. In fact, I'm gonna show you a demo of how it's happening. But I'm not going to show you through this API because it's really hard to see what Tornado does underneath. We can affect to change the device from the API level, right? And what I did was create a client-server application, server-client application. Let's have a look at the server. It's very simple. It's just to show a quick demo. So the server will instance a socket. And then what we do is it will create a task schedule with one task and will run vector addition. That's something simple. And in the run method, it will wait for the client to tell in which device you want to run. And we can do this and say, give me the device. And then the task schedule, this is the object that we create for the task graph, map the tasks to these devices, right? And we can change without restarting the application. It's the same object, it's the same task graph, okay? So let's do that. Okay, let me show you. So on the right-hand side, okay, I'm gonna run this server. And I'm gonna run with debug info just to check what it's doing. On the that's on the left-hand side, sorry. On the right-hand side, I'm gonna run the client, okay? Run client. And the client is just printing, okay, it's waiting for a device, right? So let's run on device 0. It's compiling the expression, and it's gonna run on the NVIDIA GPU, interesting. So now let's say, randomly, device 3 is a multi-core, it's the same expression because it's an object. So because it's the first time we're gonna run on that device, we have to recompile the code, right? But the execution is migrated to that device. Let's say use device number 2 is gonna run, interesting, on the Intel graphics, right? And device 1 is 1. I think I have 4 for the OpenCL driver. And now if I switch back, the compilation is not triggered because the code was already compiled. So I can stay, let's do 2, let's stay to 3, let's stay to 0 again. And the code is already migrated, right? So it's a nice tool. Okay, so I hope I convince you that we can do this. Now, a final words, we're approaching to the final bit. I want to highlight one thing. So since we have the ability of doing this compilation for heterogeneous devices in background, we got the following idea. So Java, you might already know this, right? So if you run Java, pure Java, you start by running on the bytecode interpreter, Java interpreter. If you run multiple times on the bytecode interpreter at the method level, most likely you're gonna trigger a JIT compiler. If you're using hotspot, you're gonna trigger either C1 or C2, most likely C2 nowadays. And if you're using Graal, you're gonna trigger Graal compiler. But once the code, let's say you're using C2 or Graal, is already generated, the optimized code, you cannot get faster. It's not possible. However, well, as far as I know. However, if you plug in the dynamic reconfiguration, right, you might get the code faster after all. For example, you can go from C2, stay with C2, then later on switch to a multi-core. The Tornado runtime will decide for you, and then later on switch to the GPU. Why is this switching? Well, it really depends on the input size. If you're running very small data sizes with multiple computation, most likely we'll stay with C2 because they do a very good job. If you have an application that matches the applicability of the accelerator, you're most likely gonna switch to that device. And this is important message they're gonna get through. I'm not saying let's use the accelerator, yes or yes. I'm saying use accelerator when it makes sense to use it. In fact, Tornado will decide for you. Why? Because if you have a very branchy code, maybe the GPU is not good suitable for you because GPUs don't have branch predictor, for example. So stay with C2, stay with Graal, JIT compilation, because they do a really, really good job optimizing the code. But for other applications that we can detect data parallelization or pipelining and so on and so forth, switching to accelerator makes sense, right? You can get good speedups, right? Right, so let me show you the dynamic reconfiguration in action. So how to read this graph, I show you two benchmarks, DFT, the one I showed you at the very beginning of the presentation, and Embody, typical simulation for physics, astrophysics. The x-axis show input size, while the y-axis shows speed up against Java hotspot. So the line shows the ability of TornadoVM to switch itself. So it will decide for you. And then the dots or squares and so on is I'm not gonna switch, I'm gonna stay with Tornado on this device forever. So let's pick, for example, DFT, this one, end-to-end. I'm using end-to-end policy. And you can see that for small data sizes, Tornado will stay on hotspot, will not change. Will say, no, look, I'm running very small data size. It doesn't make any sense to switch. However, as soon as you increase the data size, TornadoVM, well, you can switch, actually switching. You can get either a GPU or a multi-core, right? And interestingly, let's take a look at the peak performance one. If we take the policy of peak performance, you will start running with this multi-core, and then we switch to the GPU. So assuming that the GPU is always faster is not the case, right? It really depends on the input size, how is the code written, how is the code generated, and so on. And the speedups you can get are really high. In fact, DFT, for example, gets more than 4,000x compared to Hotspot. We have a publication for this, so you don't have to trust me. You can read the paper, you can reproduce it if you want to. In fact, well, we have a lot of publications in our repository. So just briefly to talk about related work, I think was a question that already spotted this thing. Sumatra is one of the, I think one of the first one. It's not the first one, but I think it's the Java is a well-known project. We took ideas from Sumatra. There's another project called Marawak. It's not famous at all. It was my PhD thesis, by the way. But I want to highlight a few things. So I split this into several categories. The devices that they support. So TornadoVM support more devices than the rest. The ability to perform live task migration. So as far as we know, there's no other framework in this territory, let's say, that can perform live task migration across GPUs and GPU and FPGAs and so on. Compiler specialization, there are not many, actually, the one I implemented back then, plus Tornado. And the ability to support dynamic languages. In fact, Marawak. And there's also another one called CUDA. CUDA is not for Java. It's a framework that is built on top of Truffle. And you can get any Truffle language on GPU, on CUDA, so NVIDIA GPUs. However, the way to write the kernel is still CUDA, be aware of that. While in Tornado, you write Java, okay? I think the reference ones are Sumatra and Aparapi. Aparapi, I think, is the most common one. I think people are actually using it. You can target multi-core and GPUs. I think there is some research work around FPGAs. It's not integrating in the master branch, but I think you can get it. But it doesn't perform live task migration or compiler specialization, or as far as I know, it doesn't support dynamic languages. Okay, so just a few notes about future work. So right now we are integrating a new API. Actually, it's coming next month, mid-March, around mid-March. And we are in a collaboration with Intel Labs for providing a new backend. So right now we have two backends, OpenCL and PTX. And we're building a new one for SpeedV. This SpeedV is a standard as well by Kronos Group. And this is a binary format to represent compute kernels. And with that, we can access also integrated GPUs by Intel. We can optimize further. We can apply better optimizations. And in the future, we want to apply energy policies. Why am I telling you this is interesting? Because when we perform task migration, for example, we can say, well, do the task migration, but instead of having a performance platform in mind, do the migration because the platform you're going to migrate to consumes less energy. And this is really interesting. So we want to work on that. It's still future work. Right, so just a few words about how Tornado is being applied in industry and use cases we have. So we have some work around deep nets. Deep nets is a framework, Java framework for deep learning. And I show you here some results we have been collecting. So we have been able to accelerate a specific function from the deep nets pipeline framework on various GPUs. And if we get end-to-end, we can get 7x, 6x performance. And if we compare just the kernel time, we can get up to 90x performance by running on GPUs. You can get the details from one of the latest publications we have. Also, Tornado is being used in industry. And we have cases from many different domains. For example, a company in London, Exus, is using Tornado for machine learning. I'm going to tell you more details in a bit. Also, Neurocom is a company in Luxembourg, is using Tornado for processing natural language processing and fintech. Okay. There's another company in London for security. They are applying Tornado for computer vision in this case. Also, Sparkworks for smart buildings, or even for optimization for vehicle routing is a company in UK called Optrack. So just to give you a few details about this, Exus is the one that using deep learning, machine learning. And what they are doing is actually quite interesting. Apparently this experiment that if you go to a hospital, there is a chance to go back within a very short period of time, right? So it's a high chance to be readmitted. So what this company is doing is to have a machine learning model that can predict how many patients are going to be admitted to hospital, so they can reorganize the staff that they need for a particular hospital, right? So they don't get, overloaded. So they have a machine learning technique here they're applying for accelerating 2 million patients in a training model of the machine learning technique. And so far they have been able to accelerate from 2,000 seconds in the training mode to 100 seconds, to 180 seconds, to a speed of 14x. It's nice speed up. Then this company, iProof in London, actually the use case is provided by Gary. Gary is the creator of Aparapi. He used Tornado for accelerating face detection, okay, through the cascade algorithm. Basically, it's just in a picture, recognize how many faces there are. And so far, he got like 24x performance on a CPU multi-core. It's a big multi-core machine. And you can get the details following this link. So he's explaining step by step how it's built, the conclusion he reached with Tornado, and so on. Also, we are integrating Tornado with other frameworks like Flink. Not sure if you know Flink. Is a framework, MapReduce framework for stream processing, streaming. And basically what we do is in the compute node, we are replacing standard JDK with the JDK plus Tornado in order to accelerate user functions, UDF functions, if we have the hardware in there. So this project is about to finish. So we hope to publish results within 15 days, maximum 1 month. We will have results for this. It's a very exciting project. So as promised, just to sum up, so TornadoVM is an open source project. It's fully open source. It's on GitHub. You can download it. You can check it. You can contribute if you want to. If you want to try, if you want to try, we have Docker images. I think it's the easiest way to try. It's just pull the image and just run it, right? And we have Docker images for NVIDIA GPUs and Intel GPUs, if you want to give a try. We have a team. Obviously, I didn't build this myself, we have a big team. Well, it's not a big, but we're growing. Mostly we are academics. So Christos Kotselidis is the principal investigator of the group. And we are looking for collaborations. We're looking for collaborations either in industry or in academia. And we're open also for feedback. So if you want to talk to us, we're very open. We're collecting feedback. We're collecting comments. Actually, for example, a new API we're building is based on the feedback we got, right? So we're happy to get that. And please talk to us. So takeaway, I hope I convince you that now heterogeneity are everywhere. Heterogeneous hardware are everywhere, okay? That's good. But we need a way to handle, to program those hardware efficiently. One of the proposals we do is through TornadoVM. So I hope to convince you that, TornadoVM is a really nice tool. It's a really nice framework to get quickly access to GPUs and FPGAs with minimal effort. Also, I hope convince you that we can perform task migration, and that's a very powerful tool and nice to have concept in there in Tornado. And we can get really high speedups. Right. So with that, I conclude my presentation, and I think we have a bunch of questions already, which I'm really happy to answer. So thank you very much for your attention.
And thank you. And in addition, we're going to burden you with some questions, a bunch of questions.
Yeah, that would be fun.
The first one is, would FPGAs have a high impact on blockchain and crypto mining?
Yeah. So sorry, I didn't get the question. So it was a statement, or?
Would FPGAs have a high impact on blockchain and crypto mining?
Well, it's customized application for the hardware, right? So on the so for Bitcoin, people are using GPUs or ASICs directly. It's true that building ASIC is more expensive, so getting the application down to an FPGA it might be good, right? However, I still believe that GPUs get more usability in that terrain, more speed ups maybe, because it's easy to adopt the code, to change the code, right? Unless the code is totally fixed, of course, go for FPGA, yes. But it's a niche terrain for many applications, many domains.
So what other languages will follow after Java for FPGAs? For example, would Google's Go have any advantages over Java because of out-of-the-box parallelism?
Yeah, so in Tornado, apart from Java, I mentioned a few during the presentation. We can run Python, R, Ruby, JavaScript, Node.js, basically any language on top of Truffle, right? We go through Truffle to get access to dynamic languages. And that's where we can target any other language, basically. You can target even LLVM if you want to, because there is an LLVM interpreter for Truffle. Apart from that, I have to say that we focus on Java for now. We have some plans. Actually, we have internal discussions to provide really native support for R or Ruby or the other dynamic language. In fact, I had a proof of concept that I developed during my PhD that I can use directly R, not Java, just R, and getting access directly to the GPU, right? Through GraalVM stuff. So we have plans to reproduce that research and incorporate it into TornadoVM. But right now there is no direct plan. We have some discussions internally to do it. Yeah.
So you
Did that
mentioned,
answer the question?
yeah, you mentioned Node.js, and that's JavaScript, dynamic language.
Mm-hmm.
Does that give you an entree into the other dynamic languages, or is there some roadblock?
Yeah, well, we have some demos showing JavaScript and Node.js. Just an example, right? Our main target right now is Java, I have to say.
Okay. Will there be a disruption of FPGA offered as cloud offerings by Intel, NVIDIA, or other major semiconductor companies?
So you're referring that as a future or as a present right now?
Well, a disruption. A
disruption. Okay. So I had to say that, thanks for the question, because Tornado can run out of the box on Amazon Cloud, right? So if you want access to the FPGA on Amazon with Xilinx, you can access it. And in fact, you have documentation step by step how to get access to the Amazon and set it up. Now, if the future is putting more effort on FPGA, I believe that. I truly believe that. Why? Because, well, FPGA is a very attractive hardware. You can get a hardware configuration and change it dynamically. It's true that maybe compilation takes time, or maybe the configuration will take time, but it's very attractive for many companies. Not only for acceleration, but also a custom algorithm or routing or this kind of stuff. And I see trends from Intel and AMD going in that direction. Yeah.
So what about FPGA's impact on security and encryption?
Yeah, well, I'm not an expert on security, but that's one of the main purpose of right now, or main usages of FPGAs. I think it's getting more impact, or more, it's getting famous. It's going to that direction as well. Also for data centers like routing, for example, custom algorithms for routing.
What about negative impacts we've got?
Negative from FPGAs.
Easier for malicious operatives to.
I mean, from the research perspective, I can tell it's difficult to get a very fast configuration on FPGAs. It's extremely hard. So in fact, going from high-level languages, map it down to the FPGA is a lot of work. It's a lot of work to achieve performance, right? That means that we still need an effort from humans, meaning that the negative impact will mean that, okay, we're going to down from high-level languages down to the FPGA, still it's going to take some time to being adopted properly, right? Because the complexity to optimize that specific for those hardware. However, we're actually in talks with companies about how to get access, sorry, how to get more efficient code on the FPGA. And it involves a bit of human effort and the compiler effort. So it's kind of a mix between the two. It's a kind of synergy between the knowledge from the actual experts and the knowledge we can take from the compiler to get down. So I would say that the negative, just to summarize, part will be that thinking that the FPGA is going to be the only solution, okay, everything is going to be through FPGA. This is going to take time. I don't know if you've been sure. I will say use the accelerator when it makes sense to use it, right? That should be the right approach. For example, GPUs are very good at exploiting data parallel applications, and FPGAs are very good at exploiting pipeline parallel applications. So if you are targeting something different, well, you can run it, but maybe it's not efficient, right?
So each graphics card manufacturer has a different history with open source. Has NVIDIA assisted or talk about that? But what about TornadoVM working better on one platform than another? The platform differences.
Yeah, well, referring to your question for NVIDIA, we don't have any help from NVIDIA. We just built it ourselves from scratch. So we start with OpenCL backend because OpenCL is a standard and many vendors implements OpenCL. The main ones are Intel, Xilinx, AMD. Then we see a trend that I believe, I don't know if the right thing, but it seems like there's a trend to stop OpenCL for evolving. And there are other alternatives. One of those could be SPIR-V, right? Still, you need an OpenCL model. You might need an OpenCL model underneath to run SPIR-V. So we are moving toward other backends like SPIR-V. With NVIDIA one, we take that and say, okay, sometimes you can better optimize the code for NVIDIA instead of running for OpenCL, going to PTX. And actually, the demo today, I show you that we can get better speed from PTX. And that's the reason we include PTX. Having said that, we don't focus on just one particular backend. We want to expand and have many possibilities. As a research project, we want this to live long as we could, as long as we can. And OpenCL, because it's a standard, was very promising. We're gonna keep forward for pushing for OpenCL, but we are opening more backends, and you can plug in your own backend if you want to, right?
You may have answered this already, but what's the largest number of FPGAs, GPUs that have been tested?
Yeah, sorry, can you repeat? I have trouble
what's garbling my words. What's the largest number of FPGAs or GPUs that have been tested so far?
That Tornado can run at the same time?
Yeah.
Right, so right now, if you check the code from the public repository, you can run at the same time a task graph on one device. So we assume that all tasks are gonna run on one GPU or one FPGA. However, we have work already, and we hope to publish around this year, maybe early next year, to run on as many devices as we have available in the system, meaning 4 GPUs, 3 GPUs, or even they can be different models like CPU, multi-core, GPU, and integrated GPU. So far, with this combination in our lab, we have tried with 2 GPUs and multi-core together. Yeah, I think that was the configuration we have tried. Yes. Yeah. But it's a proof of concept. So I think never stop us. If that works, we can get up to 4 GPUs as well in the same system. Yeah.
And I have just a few more questions here if you have a moment. The TornadoVM might allow us to do real-time training in machine learning.
So what else can do, you referred to? Yeah, so I'll point a few, I think was at the very beginning. So Tornado, apart from machine learning, deep learning, computer vision, you can target other applications from different domains like physics simulation, mathematical simulation, for example, Embody, this kind of code, DFT for signal processing as well. Also application from fintech. So I showed today a demo with Black-Scholes that is common algorithms in fintech domain. So the main target, let's say, is pretty much whatever we can put on GPUs and FPGAs, well, good for. And those domains are critically computer vision, graphics processing, rendering, basically, machine learning, deep learning, fintech, physics simulation, this kind of stuff. So really, really different domains. I think it's enough to matter, right? Yeah.
What about in phone cameras, for example? What kind of impact would it have on imaging and digital signal processing areas?
Yeah, so I already showed the DFT, for example, the demo I showed today was exactly designed for DFT, was digital signal processing. And depending on the hardware, for example, the FPGA, we get high speed ups because the hardware provides utilities at hardware level to take advantage of digital signal processor, right? So Tornado knows this and can take advantage of it, right? So that was an example. So the main point is if the hardware allows, you can run it, and if the hardware has custom, the circuits to accelerate those specific functions, Tornado can handle it. Yeah.
Good. Well, with that, I'm going to hand it back to Sai, and we'll.
Sorry.
I am going to hand the baton back to Sai.
Yep.
Okay.
Thank you. Yeah. Thank you very much, Barry. Thank you, Juan, for that very insightful presentation on TornadoVM, and you took us to great depths on how to use TornadoVM, and you showed us a lot of live code, and also you spoke about a lot of applications. I mean, it looks like there's a lot you could do. Essentially, everything that you could do on software can now can be reimagined and re-envisioned to run on hardware side as well, which is pretty amazing. And you'll probably see immense improvements in performance, right? So really appreciate your talk and your time. I know it's like past midnight for you, and you've been awake and patient, and you've answered all our questions with a lot of detail. Really appreciate your time and help here. So it's great. I think we had an amazing session. Thank you all for joining in today on YouTube and on the chat, and for all the wonderful questions that was asked. So again, so please follow us on Twitter. That is at NYJavaSIG, and you can find out about all our upcoming events on our javasig.com website. And with that, thank you very much to Juan, Barry, Frank, and everyone here today who joined us, and all the participants on chat. Have a fantastic evening. Thank you all. Bye.
Thank you. Thank you very much. Thank you.